In this video, we are going to derive the electric field due to a dipole. So in this setup right here, we have a dipole of charges positive q and negative q separated by a distance d. And so if you recall, dipole moment is just equal to the value of the charge q, so basically the positive q, times the distance between the charges d. So if you recall, p is equal to qd, and we're going to say that we're given the dipole moment of our dipole, p. And we want to find the electric field due to the dipole at this point right here. And we're going to say it's horizontally aligned with the dipole at this point, at a distance z from the center of the dipole, right? So we're given the dipole moment, p, and the distance z from the center of the dipole. So these are the two things we were given. We want to find the electric field due to the dipole at this point. And also, we're going to say that the distance to the dipole is really large compared to the distance between the two charges in the dipole, right? So basically, the distance d is insignificant compared to z, right? And that's the idea. So how do we actually figure out the electric field at this point? Well, really, we're thinking about the electric field due to point charges, right? The electric field due to this positive charge and the electric field due to this negative charge. And so if we're thinking about the electric field due to this positive charge, well, electric field from this positive charge is going to point away from it, right? And so the electric field would point to the right if we're thinking about this positive charge. So this is the electric field due to the positive charge. So we're going to call that E positive, right? And for the negative charge, the electric field would point towards the negative charge. And that's the idea. So this right here, we're going to call E negative. Now, to find the electric field due to the dipole at this point, well, really, this is like a combination of vectors, right? Because electric field is a vector, so basically we're adding these as if they're vectors. So really, to find the electric field at this point, basically we're thinking about the magnitude of the electric field at this point. So we're just going to take the magnitude of E positive and subtract it by the magnitude of E negative. So E is equal to E positive minus E negative. And basically, these are electric fields due to point charges, right? And if you recall, the electric field due to point charges can be found by this, right? The electric field due to a point charge, which I'll just denote as the point charge, right, is equal to kq over r squared, where q is the value of the point charge, right? It's basically this is the magnitude of the electric field. So the q is the magnitude of the point charge, and r is the distance between the point charge and your point of interest. So that's the idea that we're going to apply for E positive and E negative, right? So for E positive, basically this is just the electric field due to this positive charge, right? So we have kq, right, because our charge is q, divided by r squared, right, divided by the distance to that positive charge squared. And now the distance is really, all right, so here's how we have to think about it. Basically, it's this distance right here, right? Which is z minus this distance right here, okay? And this distance is basically half the length of the dipole, d over 2. And the reason why is because z is measured to the center of the dipole, so this length has to be d over 2. So really, the distance to the positive charge is z minus d over 2, right? So z minus d over 2, right? And since it's squared, right, we got to square it. So we square that. That's pretty much the idea. And then we subtract by E negative, which works the same way for the electric field due to a point charge. It's just kq, all right? Now, even though this is a negative charge, remember, we're subtracting by the magnitude of an electric field, so we're making sure that our charge is a positive, right? So we're making sure we're subtracting by the positive version of the charge because we're subtracting the magnitude of an electric field. So we got to make sure we use the magnitude of our negative charge, which is just q, divided by the distance to the negative charge squared. And that distance is basically going to be z plus this distance right here, which this distance right here is also going to be d over 2, right? Because it's just half the length of the dipole, right? And so the distance to the negative charge is just z plus d over 2. So that's what we would get in our denominator, right? Z plus d over 2. right? And of course, we have to square that. So this right here is basically the electric field we have to evaluate. Basically, you have to make sure we get this such that it fits these conditions, right? We need to make sure it's in terms of P and Z, and we apply this condition as well, right? This length Z is way greater than this length D, right? The distance to the dipole is way greater than the length of the dipole itself. And so we have to make sure we apply these two conditions, making sure it's in terms of P and Z is way greater than D. So how do we do that? Well, to make this look simpler, we're going to factor out KQ, right? And so what we're going to get in our brackets right here is 1 over this denominator, so Z minus D over 2 squared. And of course, we're subtracting 1 over this denominator, right? So Z plus D over 2 squared. So this is what we have. Basically, all we have to do now is we have to combine these fractions. And the way we combine for these fractions, we're basically subtracting them, right? We're subtracting two fractions. And so we're combining them such that we can do that. Yeah, we're doing this good. Okay, so when we combine them together, basically what we have in our denominator is basically this times this, right? We need to make sure they have the same denominator, so we're going to make sure this and this are in the denominator. So Z minus D over 2 squared times Z plus D over 2 squared, right? That would basically be our denominator that we could use to combine these fractions, right? Pretty much the multiplication of these two things, which we get that. So really, in order to do that, we would need this in the numerator here. So Z plus D over 2 squared, and subtract by this, and we need this in the numerator over here. So Z minus D over 2 squared. So this is basically just combining these fractions as if we were subtracting them, right? So subtracting fractions, we combine them into one fraction. This is what we would get. And so basically we're gonna simplify what we have up in here, right? So we still have KQ, and in these brackets, all right? Let's just focus on the denominator first. So for the denominator, basically let's notice how we can rewrite this. Really, Z minus D over 2 squared is just Z minus D over 2, and I'll just write this right here, Z minus D over 2, right? Right, if we were to multiply these two things, we would get Z minus D over 2 squared. And same thing for Z plus D over 2 squared, we could write Z plus D over 2 times Z plus D over 2. And the reason why this is so useful is because we can now see that we have two sets of difference of perfect squares. Check this out. I'm going to underline them to both. Can't we rewrite these two things in a different sort of way? Yeah, we can. Actually, here's the idea. Yeah, we're going to rewrite it here right now. So basically this, the way we could rewrite this, if you remember from difference of perfect squares, I'm going to write a quick note right here. Basically, if we have something in this form, a minus b times a plus b, then this is the same thing as a squared minus b squared. And so we're just going to apply that idea to what we're doing right here, right? This is just going to be z squared minus d over 2 squared, right? Which is just d squared over 4. So d squared over 4. So that's what we would get for these terms. And if we were to multiply these together, we would get the same thing, right? So we would get z squared minus d squared over 4, right? Because this and this are identical, which means it's basically this squared. That's all we really get. So we get z squared minus d squared over 4 squared. And so that's the idea of what we're going to get in this entire denominator. So let's just rewrite that. Basically in our denominator, we're just going to rewrite our denominator. So z squared minus d squared over 4 squared. So in our denominator, we get z squared minus d squared over 4 squared. That would basically be our denominator. Okay, so this is what we have. Now, as for our numerator, right? Now we got to look at our numerator. Basically, this is what we have in our numerator. And basically, we're expanding out things that look like this. So here's what they look like, right? They look like this. If we had something written in the form of a plus b squared, and we have a minus b squared. So a minus b squared, right? Because this is a plus b squared, this is a minus b squared. But really, this is, we know this is a squared plus 2ab plus b squared. And for this, it's a squared minus 2ab plus b squared. And so we're really applying these two ideas to our top. So for the first term, right, our first parentheses is going to be z squared, right, plus 2 times this, or just plus, right, basically plus, this is going to be 2 times z times d over 2. The 2's cancel out and you're left with zd. So plus zd plus d squared over 4, right? Because when you square d over 2, you get d squared over 4, right? That's what we would get for the first term. And for the second term, this is what we have here. So basically, we're subtracting by whatever we have here. And basically, when we expand this out, it's basically as if we're expanding a minus b squared out, which is going to be z squared, right, minus 2 times this, which is just minus zd, and then plus d over 2 squared, which is just d squared over 4. And so this right here is basically what we would get. All right, so that's what we have. All right, continuing to expand this out because we got to keep going. So KQ, basically here's what we're going to get, right? We still have z squared plus zd plus d squared over 4. All right, and distributing the negative sign, we get minus z squared plus zd, then minus goes to this, minus d squared over 4. So that's what we get in the numerator, and we still have what we have in the denominator, z squared minus d squared over 4 squared. And so the numerator looks like a mess, but really we see that some things will just cancel out, right? So in the numerator, we get some things to cancel out. And so notice how z squared will cancel out with minus z squared. So z squared minus z squared will cancel out. We have plus d squared over 4 minus d squared over 4. That will cancel out. And so really we get zd plus zd, which is just 2zd, right? So basically rewriting this, we get kq times, right? Basically in the numerator we get zd plus zd, which is just 2zd. But what about in the denominator? At this point, we're able to apply this condition right here. Z is way greater than D. If Z is extremely big compared to D, then you could treat Z as if it's just some ordinary number and D as if it's like really, really tiny, which means if Z matters, like we have, like if Z is a value 3 and D is a value of like 0.000001, then that term would not matter. We want D squared over 4 doesn't matter if D is insignificant compared to Z. So really what we get in our denominator is Z squared squared, or Z to the power 4. That's where we're at now. So we see that electric field is really, if we were to look at this, when we get 2 KQZD, right? KQZD all over Z to the power 4. And so notice how we have Z over Z to the power 4, which is just 1 over Z cubed. So really we get 1 over Z cubed. So we get Z cubed in the denominator, right? And one more thing, we need dipole moment, right? Well, check this out. Notice how we have QD. QD is just dipole moment. And so we see how we're going to get P. And so we did get a P right there. And so this right here is the electric field due to a dipole. There it is. That's pretty much what it would be. And we're assuming that this is horizontally aligned with our dipole. And we're assuming Z is way greater than D and this is the whole idea of what it would be, right? The electric field due to a dipole, and that's pretty much it.